Okay, so this is the last part of exercise 10 where we're now looking at the Newton-Raphson method for calculating a square root. In the previous two video recordings, we start out with exhaustive enumeration. We saw that would converge for an answer in many cases, but was extraordinarily slow. We now looked at bisection, which was able to cut down the number of iterations in our loop, or the number of values that we tried or guessed, just dramatically. For 144, we were running this with 11 million iterations, and we cut that down to around 20 to get the same answer, or just as reasonable of an answer. It's still off by a little bit. Now we're going to take a look at a little bit more complicated method, and I'm going to save the derivation of the equation for the textbook. It's in section 3.5, but I'm just going to update the code a little bit to run this, and it's actually a very small and simple update over the bisection. So the bisection method required a high and a low, and it based its answer off of high and low. It based its next guess, right, down here and also here, on that bracket, right? So the idea was that we were going to bracket the answer. The Newton-Raphson method actually takes advantage of solving. It's really aimed at solving for roots of polynomials, and it does not actually need a bracketing approach. It successively guesses better and better guesses based on the derivative of the polynomial. And again, I'd urge you to read through the book and kind of understand a little bit more about how we're doing that. So here, the first guess is just going to be, it very well could be x, but x over 2 is a nicer guess. It's a more reasonable guess. And if we think about that, that should make sense. Generally, all numbers or all square roots are probably going to be less. The square root of x for any x is generally going to be less than half of x. So that's a pretty good first guess. But more importantly, the selection of the next guess has to do with the difference between the current value and the answer that we're trying to find. So I'm going to update my formula, and for Newton's method, the formula for coming up with the next guess is the original, or the previous guess, minus a factor. And that factor is answer squared minus x. All right, so the difference between the value that we're looking for and our answer squared. This would be also equivalent to epsilon, right? Divided by 2 times the answer. Okay, so just kind of making sure I got my parentheses in order here. Okay, so we got that, and then we've got all of this. I think I'd like to put those in parentheses as well. Still counting the number of iterations. Of course, we want to say Newton's method instead. All right, so let's give this a run. Oops, I have a missing, looks like I have a missing parentheses here. Okay. And let's try 144. We get that. Now that's 6 iterations as opposed to 20. That's nice. That's pretty good. That's 20 iterations is pretty instantaneous, but 6 is better. For 511, I was getting 7 iterations as opposed to 21. To 1, 2, 3, 4, 5, 6, I'm getting 11 iterations as opposed to 34. Arguably, maybe even less work, certainly a little bit more of a less intuitive formula for coming up with the next guess. It's a little harder to explain Newton-Raphson in a 5-minute video than it is bisection, but certainly excellent results. So we've seen a second improvement over calculating the square root, and in fact, when we start talking about functions, we'll learn that the math module in Python has lots and lots of functions associated with it. One of them is the square root function. It's not a magical function that can just sort of automatically find the square root of something. It uses techniques like this. It's fast, but it involves code. It involves loops to calculate those square roots.